So thanks a lot for the invitation, and to the audience, thanks indeed for your patience. I was kind of lost somewhere in the virtual space. So yeah, I'm a CNRS research director, and CNRS is a beautiful place where we can work everywhere in France, but also abroad because it has international labs. And right now, indeed, I'm based in Singapore in a lab called MajuLab, which has an antenna inside the Quantum Center, the Center for Quantum Technologies. And today I want to tell you a few words about an initiative that is currently taking off, which is the Quantum Energy Initiative, which aims to take into account the energy cost of quantum technologies while they are getting developed. And so this is something that I have co-funded with Olivier Ezrati, Janine Spletz-Teusser, that I guess everyone knows here in the audience, and Robert Whitney, Olivier and Robert being based in France. So before going into the meat of what the Quantum Energy Initiative is, I want to say a few words, like I could say philosophical words about human activities and the concept of efficiency. Here on your screen, what you see is the archetype of a human activity. You are a human being, you don't want to do the work, so you build a machine that will do the work for you. And this machine, you need to input material inside, you need to input energy, so these are the resources. And in return, this machine will execute the task that you don't want to execute with a certain performance, with a metric that quantifies actually how good the machine has performed. And with this metric of performance and this resource cost, you can build what is called the efficiency of the machine, which is nothing but the performance divided by the cost. Okay, and the purpose of science and technologies in general is to increase efficiencies. And this concept can be easily applied, and it has been applied for years to something as spread as classical computing. And so in classical computing, usually the resource that we take into account is the power consumption, and the performance, it's usually quantified as the number of floating point operations per second. So it's quantified in flops. And with this, we can build a performance per watt, which has the dimension of the inverse of an energy. And with this efficiency, we can rank supercomputers. And here you have the evolution of the megaflops per watt as a function of the years for some classes, very good classes of supercomputers. Actually, there is something that is very important in there, which is named Cummings law. And Cummings law is typically how this energy efficiency for computing, classical computing, evolves. And since the beginning of classical computing, it was shown that the energy efficiency of classical computers has doubled every 18 months. And it has saturated since 2010. So this Cummings law can be seen actually as the energy counterpart of Moore's law, okay? And this is basically due to the improvement of component energy efficiency, the improvement of architecture, and the state of the art is 52 gigaflops per watt. So now the problem is that currently the energy cost of information and communication technologies is strictly exploding. And so I used to cite this figure. You can find different kind of figure in the literature. This one is 11% of global electricity consumption in 2020. And basically, there is no expected gain in efficiency because the end of this Cummings law I was mentioning before. And we have also to take into account the fact that raw materials are also correspond to a big environmental cost. So we need for a paradigm shift, and we need for alternative technologies to store, process, and transfer information. And simultaneously, there is this this burst of quantum technologies. And so the fact is that nowadays quantum technologies, they explode, but they don't explode because we are searching for energy savings. actually what we search for is the performance in terms of computing power, basically to be able to solve big problems in a minimal amount of time or minimal amount of physical operations. And this is the promise of quantum computing. Basically, you have the computing time here, the problem size here. With classical computers, some problem lead to an explosion in the computing time, while quantum computing could allow to bring back this computing time into reasonable durations. So this gives rise to well-known concepts of quantum computational supremacy and quantum computational advantage, which corresponds to the case where a quantum computer computes much faster than a classical computer on the same useful case. So this is well known, and this is actually a big debate today to see how these concepts are resilient against the presence of noise and the fact that these quantum computers will need error correction, will need a big lot of hardware around the quantum processor to classically control it, etc. So this is well known, and this corresponds to the current challenges, I would say the most well-spread challenges of the quantum computing community. And where with the Quantum Energy Initiative we want to bring the debate is on the concept of energy efficiency. So we can basically define an efficiency as a problem size divided by the energy. And in the same way, people so far, they have run after the computational advantage, we could also run with quantum computers toward a quantum energy advantage. And we could also define, in the same way, a quantum energy supremacy, where a quantum computer would solve a problem that no classical computer could do with reasonable amount of energy, or more modestly, a quantum energy advantage, that is to show regime where a quantum computer could solve problem with less energy than best-in-class classical computers and algorithms. Okay, so these are very interesting targets which do not overlap with the usual targets people have in mind. Okay, and actually the fact that it's currently quite overlooked, this problem, by current national strategies for quantum computing. A proof is that if you launch the question in an assembly, do you think that the quantum computer will cost a lot or on the contrary will allow to save energy? You find half of the answers for and half of the answers against. And this is symptomatic of the fact that there is currently no proper framework, no proper methodology to treat and to answer this question. And this motivated this paper I published last year, Quantum Technologies Need a Quantum Energy Initiative, and then the launch of the initiative by itself. So the diagnostic that we had when we launched this initiative is the fact that there is no methodology. And there is no methodology because this is an interdisciplinary challenge to work out energy efficiencies for quantum computing. And why is that so? So here you have this complicated graph here that is actually a scheme of the full stack of a quantum computer, which starts with the upper part of the stack where there is the end user here that defines a use case, a problem, that gives rise to the writing of an algorithm that is then compiled, gives rise to an architecture, and this architecture then is brought onto a quantum circuit, is translated into a quantum circuit, okay? So this is the upper part of the stack, which is usually hardware agnostic. And on the lower part of the stack, you have the quantum processor with all the macroscopic devices to control the quantum processor, whether CMOS or cryogeny or whatever you may think about that help you to design the classical context around the processor. And this is usually the realm of enabling technologies with in the middle the pure quantum physics, okay? So this defines all the, I would say, expertise that we need to optimize an energy efficiency. And we really need to articulate all these stacks. And because of the fact that, like I said, an efficiency is a metric of performance divided by a resource cost. The metric is usually defined at the level of the quantum processor, and it is the result of a big fight between control and noise. But this emerges at the quantum level, while all the resources that really matter, they are defined at the macroscopic levels, and they are either hardware agnostic or hardware dependent. So we need to put in synergy all these expertise. And that's precisely the purpose of the Quantum Energy Initiative. So here is the timeline of the initiative. So the vision paper was published in June. We have launched the website and the manifesto, well, on the nice and very fruitful advice of Tommaso Calarco. I don't know if he's still in the room, but he is one of the fathers of this initiative, and we thank him for that. Then actually the process gained very good momentum. In January 23, concretized in the creation of a board that you see here that is representative of the different areas of knowledge that we need to, end up with useful results. Then in May, we had actually a workshop, the first meeting of the working group on quantum energy initiative that was created at the IEEE and that I'm chairing. And in June, I'm happy to tell you that we have reached more than 300 participants spread over more than 48 countries, and we have 29 partners at the level of different government organizations and research organizations and companies. We plan to launch a YouTube channel in July, and in October, there is a deadline to a cost network that we will quite probably apply for to start having conferences together that on a regular basis. But in between, the first workshop is already scheduled. It will take place in Singapore in November 2023, and registration without contribution will soon be open. So, and here are the relevant website for the initiative and for the first workshop. Here is a view on the first partners that I was telling you about. So research organization, industries, HPCs, and cloud service providers. And the key scientific questions that we want to address are typically gathered on this slide. Can we find a quantum energy advantage? How different is this quantum energy advantage from the usual quantum computational advantage? And I'm telling you, it's different because optimizing time is not optimizing energy. We can search for the fundamental minimal energy cost of quantum computing. We can, and this search is really motivated by the fact that we want to avoid energetic dead ends on the road to large-scale computing. And this starts with computing, but obviously we want to extend this kind of thoughts and questions to all quantum technologies, and namely quantum communication and quantum sensing. So our goals and missions, they can be summarized in this way. First, we want to really create this worldwide community that is cross-disciplinary. So we want to create a new transversal line of research and collaborating project because, like I said, it gathers fundamental research and industry, software and hardware, physics and information. So, and all these experts must be gathered to work together. And we want, based on this concentration of experts and roadmaps, propose optimization methodologies, frameworks, and benchmarks for quantum technologies in general, enabling technologies, and software engineering. Obviously, we want to cover all qubit times, all programming paradigms from fault-tolerant to NISQ, and other quantum technologies. So I'm telling you a lot about methodology, but actually we have like a first try that we have proposed in my research group, which is CET, like Quantum Energy Team. And so in our jargon, we have called this the metric noise resource methodology, because it's all about targeting a certain metric of performance, fighting against noise, using some given amount of resources. And the whole point is to make a clean assessment of these three parameters to perform basically what could be always brought back to an optimization under constraint. Okay, but so this is all summarized in this paper. Here, I'm just giving you the flavor of what we've done, and especially Marco Felusasiani, who was kind of a hero in the sense that he learned at the same time fault tolerance and the conduction of Kapton wires, so which is something like fills me with admiration. This is really a interdisciplinary work, this PhD thesis. And so we have tested our methodology on a very ideal example of superconducting qubit processor in the fault-tolerant paradigm. Okay, and what we have searched for are the conditions for a quantum energy advantage. So basically, we have computed minimal energy consumption, taking into account, again, the full stack of the quantum computer, including the cryogeny, the conduction wires, the classical dissipation due to the CMOS that are inside the cryostat, these kind of models that have been put and connected to a performance of the quantum computation. And here in this specific case, the computation that we have modeled is the breaking of a RSA-K with 829 bits. Okay, and what was computed by Marco was the power and then the energy that was consumed by a classical supercomputer based on some INRIA measurements that were conducted in 2021, which was of the order of the megawatt, as you can see. And he has modeled what would be the consumption of a quantum computer with top quality qubits using a concatenated 7-qubit code. And already with this code, which for the specialist is terribly resource consuming, we found an energy advantage by like 3 orders of magnitude. And obviously, we also found the regime of supremacy by picking up the problem of breaking RSA with a 2048 size K, which obviously represents too much energy for a classical supercomputer because it also represents too much time. And for a quantum computer, it remained in the range of megawatts. And where I want to conclude now is what is the difference between energy advantage and computational advantage? Because quite often when we talk about this call for a new research line, we get answers in the spirit of, but look, we are already trying to minimize the time of the computation. So basically, it's equivalent to minimize the energy of the computation. And to which I usually answer, yes, it's true what you say if the power is constant. But it's not the case. I mean, if you choose to optimize energy, again, you don't choose to optimize time. So we have searched in a kind of more rational and objective way the relation between the quantum energy advantage and the quantum computational advantage. And if you still have a bit of brain at this end of this long morning, you can have a look at this plot where we have actually here modeled the computing time for a classical computing here, always for the same use case, and the computing time for different kinds of quantum processors. And here you have the energy efficiency. And what you can see on this slide is the energy advantage that can be reached for size of the key that are smaller than for the computational advantage. So in other words, there are regimes where the energy advantage could be reached before than the computational advantage. And this could, for instance, open horizons for NISQ era, where it's still very difficult to show that there is a computational advantage, but maybe there is an energy advantage. And either way, maybe at some point in our history, it will be more convincing to try to save energy than save time. And so that's typically the kind of message that we carry at the QEI. And that's the last slide with a little bit of advertisement for the nice workshop that we shall have in Singapore with very nice plenary speakers. And it will be soon, like I said, open for registration. Thank you very much for your attention.